Hello everyone, hope you guys are doing well. We can go ahead and get started with chapter 24 homework. Okay, first one, who discovered radioactivity? Geiger, Röntgen, Becquerel, Rutherford, Curie. You guys can find out that. Okay, which of the following is an incorrect representation of the indicated particle or nucleus? You guys can figure that one too. Number 3, which of the following decay does not produce new element? You guys can do that too. Which one of the following equations correctly represent positron decay of potassium 19? So what is positron? Positron is the antiparticle of electron. So in a positron, the mass is 0, charge is 1. And this is a beta particle, and this is the antiparticle of beta particle, where you have a 0 and -1 charge, and the electron is 0 and -1. They both have the same charge and the mass, but the beta particle are high energy electrons, whereas the regular electrons, they are not that high energy. They are the electrons that normally exist in the shells of the orbitals. Okay, so this is the beta particle. So we can find out which one is showing us the emission of a positron. Okay, positron decay. So which one do you think is the positron? This one. So since it's a decay, it has to be in the right hand side. Once you figure out, okay, I found the positron in the correct side. Now let's see if it balances. So 40 plus 0 is 40 here, and 18 plus 1 equals 19. So looks like first one is the correct answer. Select the nuclide that completes the following nuclear reaction. So you have samarium 147, 62, and helium 4 and 2. So the new nucleus that is going to form, its mass and the charge, when you add the two together, should equal 147. So 147 minus 4 is 143. So when you add these two together, it should equal to 147. And 62 samarium, so here you have 2, so then this should be 60, because 60 plus 2 should equal to this 62. So you need to figure out which one has the mass number 143 and number of protons or the charge 60. Okay, 143 and 60. Sorry, sorry, I was looking at number 6. So we are working on number 5. Okay, so do we have a correct answer there? Yes, we do. Okay, the next one, number 6. Select the nuclide that completes the following nuclear reaction. So similar to the previous one, you just have to do find the new element. Let's say that is as X. You can put X since we don't know what is the element yet, and then you figure out your masses. 123 plus 0 should be 123, and then 52 minus 1 is 51. So 123, 51. 123, 51. So you choose the one element that has the mass 123 and charge 51. Okay, that's how you do these reactions. Number 7, select the nuclide that complete the following nuclear reaction. Now with that in mind, you guys can do number 7. You guys can also do number 8. What you need to do is you have to add up the charges on the right side and see if it matches with the one in the left. Same thing for the mass. Okay, and number 8 also similar to that. Number 9, the radioisotope 9037 will decay through. So what do you think it's going to decay through? Remember, we learned in our lecture, we want to see whether it is proton rich or neutron rich. Okay, so rubidium. So what you're going to do is you're going to look up rubidium in the periodic table and find out what is its mass number. Rubidium is 85.46. 85.46 is rubidium. But what is given here is rubidium 90 and 37. So this is the atomic mass, but this is the mass given. It looks like since it, how do we get the mass? Mass is given by the addition of protons and the neutrons. So this is the atomic mass. Number of protons doesn't change, but if the mass is high, that means it has more neutrons. So rubidium is neutron rich. So in your lecture slides, and also you can see the lecture videos that we talk about, if a element is rich in neutrons, it would undergo which decay? Beta decay, neutron rich. Okay, and I also showed you how to find out whether it is neutron rich or proton rich. Even I talked about it right now. First you locate rubidium in the periodic table, find out what is the atomic mass that gives from the periodic table, and see if the given number is greater than or less. So the given number 90 is greater than the atomic mass. Mass is proton plus neutron. So this is the protons. It does not change. So then 90 is higher than 85 because it has more of neutrons. If the neutrons are rich, the isotope will decay through beta decay. And let me see if I can show you where we talked about that, so you know how we have to refer. Let me see. Okay, you see here neutron rich, nuclide type, neutron rich, and then it has a high N over Z value, so mode of decay would be beta decay. Okay, and in this PDF you don't see the negative, but when you see the sign, it is a beta decay, right? And then if it is proton rich, meaning you find the mass given is less than the mass that you find in the periodic table atomic mass, that is proton rich. So that would undergo either beta positron emission or electron capture. Okay, and if it is a heavy nuclide, atomic number greater than 83, it would undergo alpha decay. Okay. Okay, let's go back here. Alright, so that is a beta decay. Isotope with a low value of N over Z. What do you think that's going to happen? Isotope with a low value. Now the N over Z will generally decay through, which I just showed you. That also the ratio will be lower if it has, so the ratio would be nitrogen, not nitrogen, neutrons over protons. Okay, if the N over Z value is low, that means it is high in protons. That would undergo what? What did we learn? Electron capture. Okay, electron capture or positron emission. We don't have the positron emission in number 10, so it should be then electron capture. Okay, number 11, Z greater than 83. I just show you from the table what is the mode of decay, so you guys can do that. Number 12, the isotopes neon 2010, and then you have neon 2110, 2210 are all stable, while neon 2310 is radioactive. What do you think would be the mode of decay of neon 2310? Now, neon, if you look at in the periodic table, atomic number 10, what is the mass? Is 20. Atomic mass is 20. From the periodic table, neon atomic mass 20. Number of protons 10. What is given here? Neon, not helium. Yeah, it's neon. Yeah, that is going to be 23. So what do we have more in this guy? Because the number of protons 10 doesn't change, so it is neutron rich. If a nuclide is neutron rich, how would it decay? I showed you in the table, beta decay. Okay. Number 13, the isotope scandium 4221 is unstable. This is predictable because, why is it predictable that it is unstable? Now let's look at scandium 21. Scandium atomic number 21, atomic mass given is 44.95. 44.91 is the atomic mass of scandium from the periodic table, and the scandium given is 42. So the mass is less compared to the atomic mass you find from the periodic table, meaning this has less number of neutrons or more number of protons. The number of neutrons in here is less compared to 44, is too small in relation to the number of protons. So let's look at the first one. The mass number is too large. It doesn't tell anything to us. The number of neutrons is too small in relation to the number of protons. So that's the correct one. Scandium isotopes are all unstable. Atomic number is too large. Atomic number is 44.91. We cannot say it's too large. It's based on the number of protons and neutrons. The number of neutrons is too large in relation to the number of protons. So these two. But we know, we just find out that the number of neutrons, it's not too large, it's too small in relation to the number of protons. Okay. Okay. Okay, the next one. Which of the following isotopes is most likely to be unstable? Again, what you need to do here, you're going to look up and see which one has, if you do these things, okay, so here, you look up the ratios of N over Z. If the N over Z value is 1, then you know it's going to be stable. So oxygen 16:8, that's 1, N over Z. N is 16, Z is 8. Neon also 1, hydrogen also 1. And then the boron, let's see, 11 over 5. Neutrons, okay, 6 over 5. 72 minus 22, 50, 2.27. Okay, so let's look at 14, and we are looking at N over Z ratio. N over Z ratio. What's the number of neutrons in boron? Mass number 11, number of protons 5. So 11 minus 5 would be 6 over 5. So 6 over 5, 1.2. And this one, 16 minus 8 is 8. 8 over 8 is 1 n over z. This is also 1. This is also 1. What about here? Rubidium. 72 minus 37. 72 minus 37 gives you number of neutrons. That is 35. 35. Right? 72 minus 37, checking again, 35, and you divide it by 37. 0.945. So that gives you 0.945. If the n over z ratio is less than 1, that is going to be unstable. It could be a little higher like this, and perfectly fine. It exists. So the one that would be most likely unstable would be rubidium 7237, because its n over z value is 0.945. Okay. Okay, so the next one. Which of the following most likely to be unstable? So again, you can do the same. Yeah, you follow the same way that I showed you in number 14. So you will be able to find a one that would be maybe less than 1. Let me check. Yeah, do of every element, do the n over z values and find the one that will be less than 1. Then that's going to be the only unstable one. Okay. The next one, isotopes of promethium, PM, these two guys, 144 and 59, are unstable and lie on opposite side of the line of stability. Which of the following combinations is most likely to represent the type of decay for these isotopes? Again, okay. Remember I showed you how to look up what is the type of decay in these questions. Number 9, number 10, also number 12. By looking at the atomic number. So 59 is promethium. Look up what is the atomic mass given from the periodic table. Can you guys look up? I'm also looking. It is 59. I have 57. 59 is PR, atomic number 140.9. Okay, 140.9. 140.9. This is the atomic mass. Compare it with this number and see which one is high. Remember I showed you how to analyze it. And then compare it with this number next and see whether it is proton rich or neutron rich. And based on that, if it is a proton rich, you know what kind of a decay it would be. If it is electron rich, you know what kind of decay that would be. You can refer to the table I showed you in the PowerPoint slides. Okay, so try to do that for yourself. And number 17, what is the specific activity? Ci is the curie per gram of an isotope if 3.56 milligram emits 4.26 into 10 to the 8 particles per second. So I will show you how to do this one. So we want to find out the specific activity in this unit. At the end we want the unit Ci over G, and we are given that it says it emits 4.26 into 10 to the power 8 particles per second. Okay, particles per second. Now we want So this is the disintegration. Disintegration parts per second. And 1 Ci equals 3.70 into 10 to the power 10 disintegrations per second. And where do I get this number? Right here. When we talk about the decay, I showed you, over here. Curie is more commonly used unit. SI unit is the becquerel, and you can see here 1 Ci, 1 Curie is 3.70 into 10 to the power 10 disintegration per second. So we need this unit to convert Curie to disintegrations per second. That's why I use this over here, 1 Curie. Okay, and you start with what is given, which is the number of particles, 4.26 into 10 to the power 8 particles per second. Okay, and then we are going to convert this with the given unit using this one over here. We see 1 Ci equals 3.70 into 10 to the power 10 disintegrations per second. Now this second and this second over here will get cancelled. Okay, so now we have Ci over D. So now this 4.26 particles emission is normally the disintegration D. So that D and this D will cancel. This S and this S will cancel. Okay, our goal is to get it in this unit. Now we have Ci already. Now we need to convert the grams. Now it says 3.56 milligrams. Okay, so 3.56 milligrams emits 4.26. So this much of radiation is emitted by 3.56 milligrams. So we continue this unit conversion times. I'm going to go ahead and erase this part. And the continuation times, and this much of integration is happening per 3.56 milligrams. I just put 1 as the numerator here. And we want to convert it to grams. So we know 1000 milligrams equals 1 gram. So milligram cancel. So in our numerator you would end up having Curie, and in the denominator you will end up in grams. Okay. So basically the disintegration per second that is given to us as the how much emits 4.26, we are converting into Curie per gram. So you do the calculation, 4.26 into 10 to the power 8 multiply by 1000 and you divide it by 3.56 and 3.70 into 10 to the power 10. Okay, so your final calculation involve 4.26 into 10 to the power 8 into 1000 and 3.70 into 10 to the power 10 and 3.56. This will be your final calculation. Okay, all right, that will give you an answer that you find in the answer choices. Let's look at number 18. The radiochemist Willy Glove studied thorium-232 and found that 2.82 into 10 moles emitted 8.42 into 10 to the power 6 alpha particles in 1 year. What is the decay constant for thorium 232? Okay, so how do we go about doing that? You want to find out the decay constant. Now let's go back to our PowerPoint slides and I'll show you where to find decay constant over here. Rate of radioactive decay. A is the activity. A is called the activity, and which is proportional to the number of nuclei present. So N is the number of nuclei and K is the decay constant. So we're going to use this equation. A equals Kn. A equals Kn. We're going to find out K. So then the K would be A over N. A is the specific activity and then N is the number of nuclei. Decay constant. Okay, how do we go about doing that? Let's look at that. It says it emit 8.42 into 10 to the power 6 alpha particles in 1 year. That is going to be our activity then. Okay, 8.42 into 10 to the power 6 alpha particles per year. Okay, and 2.82 into 10 moles emitted, and 8.42 into 10 to the power 6 particles, that's the activity, and then the N is the number of nuclei, and that is going to be this one. Then 2.82 into 10 moles. And to find out the nuclei, the number of nuclei, if you take 1 mole, there are Avogadro number of nuclei. 1 mole has 6.022 into 10 to the power 23 nuclei present. So when you do this calculation, you will find your decay constant. 8.42 into 10 to the power 6 divided by 2.82 into 10. Am I missing something? 2.82 into 10 to the power. Let me check the original question to see if there is an exponent. Yeah, there is a 10 to the negative 7, but I don't see it here. Okay guys, if your PDF just stop at 10, it should be 10 to the power 7, 10 to the power negative 7. That's what I was thinking. Okay, good. So this should be 10 to the power negative 7 right here. Okay, I'm going to write 10 to the power negative 7. That's a typo, but it has not converted properly with the negative 7. So 2.82 into 10 to the negative 7. So do this one when you guys are doing a calculation, otherwise you will not get a correct answer. You will say none of these choices are correct, but with 10 to the negative 7 you will find an answer. Okay, and other one is 10 to the positive 6. That's good. Okay, that's all. Number 19. The isotope magnesium 2812 has a half-life of 21 hours. If a sample initially contains exactly 1000 atoms, of 2812, approximately how many of these atoms will remain after 1 week? Now this is talking about half-life, and we know radioactive decay is a first order reaction, so we're gonna use some of the kinetics that we learned previously to solve this problem. Okay, let's see. We're gonna be using first order kinetics over here. T half would be ln2 over k. To find out the, if you are given the half-life, you can find out the rate constant or the decay constant, and these are the first order rate equation. Ln n t over n naught equals negative kt, or you can use the exponent version. Nt, n here is the number of nuclei. Sometimes we can also consider it as the number of moles, like that. Okay, so we're going to use this equation. Okay, we are given the half-life. So from the half-life, we can find out the decay constant. T half equals ln2 over k. So then the k would be ln2 over t half. So you put ln2 in your calculator, it will give you 0.693, and you divide by the t half, 21 hours. So 0.693 over 21 hours is 0.033. So we found the decay constant is 0.033 per hour, and with that in mind, we will find out approximately how many of these atoms will remain after 1 week, meaning that you can consider that as at time t, what would be the concentration, and then if you know that at start of the time, what's the concentration. Initially contains exactly 1000 atoms, so A naught going to be 1000. What we want to find out is the AT. Okay, so with that in mind, we can use the first order rate equation that I showed you. We can use which one do you think we can use? Let's go ahead and look back again here. Since we want to find out NT, okay, slideshow, the current one. Okay, so we want to find out the number of atoms at a certain time, NT. So we can use this one, NT equals N naught E raised to the power negative KT. N naught is initial amount, which is 1000 atoms, and K is the decay constant, and time is the time that was given to us in the question. It's asking how many of these atoms will remain in 1 week. So 1 week is the time. So we're going to use that equation here. We can do AT equals A naught E minus KT. A naught is the 1000 atoms times exponent. Remember, we found the decay constant as 0.033 times, and this is hours per hour decay constant, and then the time 1 week, means 1 week you need to convert to hours. In 1 week, how many days are there? 7 days. Yeah, 7 days. 7 days. And in 1 day we have 24 hours. So this is 7 days. So days to days cancel, week to week cancel. 0.033 into 24. That will give you the exponent value, and it should be negative. So 1000 times the exponent. 0.033 times 27 times 24 would be 5.544. Do this calculation. This number times 7 times 24. See if you guys are also getting 5.544. And then this is negative. Take the exponent, shift ln value and multiply it by 10,000, I believe. 1 2 3 4 1 2 3 4. There are, yeah, 10,000, not 1,000. That will give you the answer for number 90. Okay. Okay, 20. Identify the missing species in the following nuclear transmutation. So nuclear transmutation, we can represent it in this form. So meaning you have a certain element and you bombard with another element. N stand for neutron, and then after the comma it means the resulting nucleus, right? So before the comma you will have the reactants, after the comma you will have the products. So it's going to be something like this: oxygen 16,8 plus neutron. So we need to know what is the symbol for the neutron. What is the mass of the neutron? 1. What is the charge? 0. And this is the expand version of this. And then it's going to form a new element. Let's put that as X. And then the hydrogen 1 1. So let's figure out what is going to be this new element. So from the left side, 16 plus 1 is 17. So here hydrogen 1, so this need to be then 16, right? And then what about the charge? Can you figure out what's the charge going to be? Charge, here you have 8 plus 0, which is 8. So this side also it should be 8. So you already have 1, so this need to be 7. So you choose the element which has this symbol with 16 mass and charge 7. Okay, that's how you do the question if you are given something like that. And that is how we normally represent transmutation, and you find this in your lecture notes. That is the last few slides of the lecture slides, which I have not made a video because it's self-explanatory about those radioactive elements, and then there's some radiations that we find in general, so you guys can read about it, but I'm explaining you what it means over here. Okay, and then the last one, identify the missing species in the following nuclear transmutation. Now it is given in the expanded form here. Again, it's quite simple. So you have 92 here, and there are 5 neutrons over here. Remember, pay close attention that there are 5 neutrons. If it is 5 neutrons, basically that's going to be, you can consider there is 5 over here, 5 times 1 5, and this is 0. And from this side you have Fm 249 and 100. So then this side it's going to be 238 92. So what you have here is X. So this is 92. So total this side is 100. So then the X, this is going to be then 8, right? And from the top, 249 plus 5. How much is 249? 254. 254. So now this is 238. So to make it 254, you take the difference between 254 and 238, and that is going to be 16. When you add these two together, 238 and 16, it should equal to these two numbers collected. Okay, so you find the one that will give you 16 mass number and 8 number of protons for the charge. Okay, that's how you do. You are given more than 1. All right. So this is going to be your chapter 20 homework.